Now it's time to do the area inside a polar graph. We're going to do this for our specific example in a minute, but I do want to talk a little bit about the general story. So we've got some sort of graph, r equals f of theta. I've got something where at theta equals 0, let's say r equals 2, then it increases, wiggles a bit, and then actually comes back down to 0 right at theta equals pi, for example. Um, and I want to just remind ourselves for a minute about how we calculated the area under a curve. This is a great place where we need to go back to, not to antiderivatives and algebraic manipulations, but back to the idea of rectangles and Riemann sums to figure out what would be the analogous thing to do here. So here, what we did was we approximated our function by a very simple function that was constant on little subintervals in order to get rectangles. So we're using a constant approximation just on each subinterval, and we get a simple shape. In that case, it was a rectangle, which is literally the simplest shape you can take the area of. But the same two strategies are going to work here. Okay, so, and I guess I should have said first, divide into subintervals. Divide. It's not going to fit. I'm going to say subintervals. Divide the entire region of integration, and that's an interval in the independent variable, into a bunch of subintervals, and then do the constant approximation and the simple shapes on each subinterval. So when we're graphing something as a function, r as a function of theta, the independent variable is theta, usually, and that's how we're gonna, that's the only case we're gonna do here. And instead of going left to right and segmenting that interval in x up, we're going to segment the interval in theta up. What does that mean? We're going to look at theta equals some constant here, and I like to use the metaphor of a radar beam coming out and detecting how far the curve is. That's r as a function of theta. So the theta is the direction the radar beam goes out in, and the r tells you what the radar returns in terms of the distance from the radar station. So we're going to have that as one value of theta, and then we're going to let theta crank a little bit further out to here. And if I was being real careful, I would do like deltas and make a distinction between like delta theta and d theta, but I'm not going to be real careful. I'm just going to say d theta. We're going to think of that as super small, so small we can sort of treat it as an infinitesimal. So we're going to let theta crank by d theta, just like we let x crank like by dx here. And we're going to see what simple shape do we get, or hopefully we're going to get a simple shape if we approximate r not as a variable on there, but as some sort of constant. Well, you know what? R equals constant is a circle, so you're going to get an arc of a circle centered at the origin. And so we're going to add a tiny little bit more area than we wanted, just like these aren't absolutely exact until we take the limit, but that's okay because we are eventually going to take that limit. Okay, so this is a wedge of a circle with subtended angle d theta, and the radius is just r, which the appropriate r there is whatever our function gives us for that theta. So, and then we just have to appeal to what's the area of a wedge of a circle. This is a great place where, one of the many places in calculus where we really, really want to use radians. And the formula is just that it's 1/2 r squared times the subtended angle. You can check that by saying, hey, if this is 2 pi, you should get pi r squared. The 2's cancel and you do get it. Okay, so that is going to be our formula for the little bit of area in that wedge. And then we just use our usual principle. The total area is the sum of all the little bits of area, just like the total area here is the sum of all the little bits from all the rectangles. And we get integral 1/2 r squared d theta. If we want to make that a little more explicit, we remind ourselves that the r is coming from whatever that function is, and it's going to be squared, d theta, and then it's going to go from whatever the smallest theta is that is in the region to the biggest. In this case, it would go from theta equals 0, radar beam sweeps around, to pi. So let's do our explicit example. And by the way, this is every time we do a new kind of integration, like when we do area between curves or volume of surface revolution, we're really building confidence with a very general idea of integrals are applied to anything where the whole is the sum of its parts, and then that goes into like multivariable calculus, and it's great to get confidence with that. So we had the function r equals 1 minus sine theta. The graph of that was this cardioid. Try to draw it somewhat symmetrically. Oh, and as usual, I'm making the mistake. Let's see. Let's go out a little further and then come back in. Okay, not very symmetrical. Oh well. One reason I should maybe make more care to make it symmetrical is that that's a really good thing to do to simplify the process of the integration. So the area. Okay, so this is a fairly simple example. There's things that can make this complicated, and I think I'll make maybe one more part of this series to do a more complicated example, where you have crossing curves, like the area between two curves in polar, or where you have something with the hole cut out in the middle. But this is pretty simple. If I'm standing here at the radar station, in any direction, this tells me how far to go out, and I'm going to get these very simple wedges. Sometimes it's nice to really convince yourself by drawing that, doing that argument once again, just in terms of a picture. Okay, here's the wedges I'm adding up. Now, the one thing that's a little bit weird here is those wedges get awfully small when the radar beam goes to pi over 2. But that's okay. That's just kind of like integrating a function that happens to go to 0 at one point, and that's okay. So one of the things we always want to do, well, let's set it up. 1/2 1 minus sine theta squared d theta. We will need to find the limits of integration. And often, but not universally, it's just going to be 0 to 2 pi. The radar beam just sweeps all the way around. And here, that would work. You can take from 0, the radar beam's here, it contacts something, contacts stuff here, happens to contact very little and generate very little area here, but then it rebounds and goes all the way to 2 pi. So you could do this as a 0 to 2 pi. I'm going to advocate using a little bit of the symmetry here. Because this is clearly symmetrical around the y-axis, it's just twice of the integral of half of it. And so to do half, a good way to do it would be maybe crank back to minus pi over 2. We can always use negative thetas up to plus pi over 2. Don't have to do that, but I just wanted to demonstrate. And sometimes that kind of symmetry is really, really useful to take advantage of. So we're going to double that. Oh, and those happen to cancel. Okay, so what is that going to be? I think I'm going to have to square out that binomial. 1 minus 2 sine theta plus sine squared theta d theta. Okay, and so each of those is going to integrate in a little bit of a different way. This, you need the power reduction or some other equivalent observation. So let me just do that real quick before I integrate it all. And so that's what plus 1/2 of 1 minus cosine 2 theta, all d theta. Okay, I need some room up here, but we're almost done. And so that's going to be theta plus 2 cosine theta. Ooh, actually, you know what? I'm going to combine these. That's going to be a 3/2. So I hate being inefficient about that. So let's do 3/2, okay? And then we just need the integral of minus 1/2 cosine 2 theta. So that's going to be minus 1/4 sine 2 theta. Do want to be careful with the signs, although sometimes things cancel. Okay, evaluated from minus pi over 2 to pi over 2. Okay, so we're going to get 3/2 times pi over 2, 3 pi over 4. Now cosine of pi over 2 happens to be 0, and at minus pi over 2 is going to die as well. Okay, let me just put in the 0 to remind myself I actually did it. Ooh, and sine 2 theta. That's interesting. That's going to die at pi over 2, and it's going to die at minus pi over 2. So this is actually very nice. and then minus a minus 3 pi over 4. And the other ones still die. And so we're going to get 3 pi over 2. So I'm going to box it, but I don't want to just walk away. I want to think, is this a reasonable answer? This thing at furthest went out to 2. Here it was 1. It's clearly bounded in a circle of radius 2. That would have area pi r squared, or 4 pi. And it's probably bigger. Let's see. It's probably bigger than a circle of like radius 1 that you would put here. And that would have pi. So somewhere between pi and 4 pi, this is a reasonable answer. So you always want to check to make sure you get a reasonable answer. Okay, for the next one here, I'm going to do one where you have intersecting curves and you have to do some equation solving before the integration.